Good morning, dear students, and once again, welcome back to our course. So far, in this series of lectures, we discussed in detail about the fundamental aspect of what exactly control system is, and we discussed the classification of control system, what is the importance of control system. Then we discussed the difference between open loop control system and closed loop control system. We also discussed the importance of mathematical modeling and transfer function, and we discussed why we need to determine the transfer function of a system. So, what exactly transfer function? It is basically a parametric function of a system through which we are trying to define the behavior of a system. Once we know, or once we have the knowledge about the transfer function of a system, we are in a position to determine its poles. We are in a position to determine its zeros. Then characteristic equation of the system we can also determine if we know the parametric function of the system. And then we can also make a comment on system stability, whether the system is stable or unstable. Then we discussed what are the different types of methods through which we can determine the transfer function for a system. For example, if the mathematical modeling of the system is available with us, we can straight away apply Laplace transform, convert that system from time domain to frequency domain, and then take the ratio of output by input. So whatever the function which we are getting as an output, that indicate the transfer function for that particular system. In the same way, it may possible that the system is represented in the form of signal flow graph. Then how to determine the transfer function for a system if it is available in the form of signal flow graph? We learned there the concept of Mason's gain formula. So how to apply Mason's gain formula to convert the representation of a system into signal flow graph into its corresponding transfer function. And then in the last 3 or 4 lectures, we discussed in detail about the concept of block diagram technique. So, what is BDT? It is nothing but a graphical way to represent the behavior of a system by using certain sets of block, and those blocks are called as functional blocks. And by applying various rules that we have discussed in block diagram reduction technique, it is possible for us to convert a system which is represented via certain sets of block into a single equivalent block, and that technique is called as block diagram reduction technique. And in that we need to apply various rules, like what will happen if the blocks are connected in series configuration or if they are connected in parallel. Then how to eliminate the closed loop. Is it possible to split a summing point or a takeoff point, whether the associate law is applicable for summing point. And then we discussed what will happen if you shift a summing point before a block, after a block, or takeoff point before a block, after a block, or even takeoff point after a summing point, or summing point before a takeoff point. And ultimately, we conclude that whatever the rule which we apply in order to solve or simplify a given complicated block diagram, the thing is that the behavior of a system before applying the rule and the behavior of a system after applying the rule will remain the same. That means the value of output, the value of feedback signal will remain the same even we apply any one of the rule. That is the only philosophy that we need to implement. That is the only logic that we need to implement while applying the concept of block diagram reduction technique. And in the last lecture, we solved uh, very frequently asked questions on BDRT as far as gate is concerned, maybe for electrical as well as for electronics and communication engineering students. So ultimately, what we learn is that suppose if the block diagram representation for a system is known to us, then first we need to identify that is it any possibility that the blocks are connected in series configuration. If yes, then club them into an equivalent gain or into an equivalent block. Then go for identification whether there is any possibility that the blocks are connected in parallel configuration. If yes, then again club them into an equivalent block gain. In the same way, if series and parallel combinations are over, then go for applying the elimination of closed loop. And after that, think whether it is possible to shift a takeoff point before a summing point, or a summing point after a takeoff point, or you can say a summing point after a block, or takeoff point before a block. That means we need to go for applying rule number 5 to rule number 10. That depends upon the uh, availability of block diagram and the connections of block in that block diagram. And based on that, the thing is that whatever the rule which we apply, the very next modified version of the block diagram must be a reduced version of the previous case. And while applying BDRT rule, thumb rule is that before applying the rule and after applying the rule, output of the system, feedback values of the system will remain the same. There should not be any change in that. If we apply in that sense, then BDRT technique is absolutely correct. And you will get the same answer if you solve the same numerical through signal flow graph or through BDRT. That's it. Now, in this particular lecture, again, we are going to solve one more numerical on BDRT, and then we will start the next topic of a course that deals with the concept of sensitivity, what exactly sensitivity is, and how sensitivity plays an important role in order to determine the behavior of a system. Maybe in case of open loop control system, maybe in case of closed loop control systems. And then we are trying to uh, derive the mathematical expressions to calculate sensitivity in case of open loop due to variation of forward path gain, in case of closed loop due to variation in both forward path gain as well as feedback path gain, that we are going to uh, do in this particular class. And in the next class, we will solve one or two numerical on sensitivity, and then we will start one of the most important topic of control system that deals with the concept of time response analysis. So not wasting too much time, let us start with our session. In the last lecture, I gave you this numerical as in homework, numerical number 7, where our objective is to determine the transfer function of a system which is represented by a block diagram shown over here using block diagram reduction technique. And I already gave you the hint how to solve this particular numerical. See, this block and this block are connected in series configuration, so we can club them and convert them into an equivalent uh, block of gain exactly equals to s square, because we need to multiply them because these two are in series configuration. Now this s square block is in parallel with this 1 by s block. Why? Because the flow of signal in both the cases is from left to right. See, here flow of signal is left to right, again here the flow of signal is left to right, and both are additive in nature. So what we need to do, we need to replace them, or we need to replace this particular block gain and this particular block gain by applying the two blocks connected in parallel configuration. So it will be like s square plus 1 by s. So this entire structure we need to replace by a block of gain equals to s square plus 1 by s. And then this particular gain will be in eliminated closed loop form with respect to this feedback path. Which one? This one. Because here we need to apply elimination of closed loop, where the forward path gain will be s square plus 1 by s, and elimination of feedback path. So here we don't have any gain, so it will be like 1. So it will be like g of s upon 1 plus y plus, because see, the nature of feedback signal is negative, that's why we need to take here positive. So 1 plus g of s into h of s, but in this case h of s is nothing but 1, so no need to take h of s. So g of s will be s square upon 1 by s, or s square plus 1 by s. So this s square plus 1 by s we need to replace over here and then solve. You will get one single block. That block will be in series with this particular block of gain 1 by s. So straight away we need to multiply that, and that will be in elimination of feedback loop with respect to this particular block of gain exactly equals to s. So if you apply that logic, you will get the final answer like this. So I gave you this an homework and I told you that you need to try this at your homework assignment, and let us check. Let us check how many of you got the same answer. Like transfer function t of s is s cube plus 1 whole divided by 2s to the power 4 plus s square plus 2s. So this will be your final answer. Transfer function for the previous case. If you are done with this, now let us try to understand a different aspect of solving numerical on block diagram reduction technique. For example, it may possible that in some cases uh, the block diagram is so much complicated that it is very difficult to solve and analyze the system by using BDRT rule. Then what we need to do, we will convert the given block diagram into its equivalent signal flow graph and then apply the concept of Mason's gain formula to solve that particular numerical. So what we need to do over here, for example, if we know the representation of system in the form of block diagram, but if that block diagram is very complicated, it is very difficult to analyze the uh, system behavior and it is very difficult to find out its equivalent transfer function. So what we are going to do, we will convert this block diagram into its equivalent signal flow graph, and then by applying Mason's gain formula, we will convert this signal flow graph into its equivalent transfer function. This topology we need to implement. So we know that if we know the signal flow graph of the system, how to convert its or how to determine its equivalent transfer function using Mason's gain formula. But we don't know. Suppose if we know the block diagram, how to convert that block diagram into its equivalent signal flow graph. So this portion is new to us. So in this lecture, first we will discuss, suppose if you know the block diagram of a system, how to convert that into its equivalent signal flow graph. And then the rest portion we already discussed in our previous cases. So how to convert block diagram into signal flow graph. So here we need to apply some simple steps through which we are in a position to convert block diagram into its equivalent signal flow graph. The very first step that we need to implement to convert block diagram into signal flow graph is identify the signals, variables, summing point, and takeoff point given in the block diagram. That will be the first step. So whenever we are having a block diagram and suppose we want to convert that into its equivalent signal flow graph, the first and the very most important step is we need to identify each and every signal, each and every variable, summing point, takeoff point very carefully. What are the variables? What are the summing point? What are the takeoff points which are available in that block diagram? That we need to identify. Then second thing is that we need to represent each of them by a separate node. That is important. Separate node in signal flow graph. Then third is represent the blocks in between block diagram with respect to a branch in between signal flow graph. So whenever we are having a block diagram in case of, or whenever we are having a blocks in case of block diagram, that blocks we need to replaced by a branch in signal flow graph, because we know that in case of signal flow graph, in between the node we are having a branch to which we are going to connect those two nodes, and then represent the transfer function of each block via gain of the respective branch. So in case of block diagram, we are having block, and inside that block we are having some value written over there. That may be a constant one, or that may be a frequency dependent one. So those values which we can treat as a transfer function for each block is going to equal to the gain of the respective branches. That is important. And if you apply this particular logic, by the end of step number 4, whatever the structure we are having with us of a given system, that represent the signal flow graph for that particular system. That's it. So step number 1, we need to identify signals, variables, summing point, takeoff point available in block diagram. Then need to represent them by a separate node. Then identify blocks connected in block diagram and represent them by a separate branch in the signal flow graph. And then whatever the transfer function available in each block, that we need to treat as a gain corresponding to branch connected in signal flow graph. That's it. Let us try one numerical so that you can understand this technique very clearly. Suppose we have a system represented by a block diagram like this, where we have summing point, takeoff point, the main reference input R of S, and the final controlled output Y of S. So here we are having some summing points. Suppose if you count here, we are having first summing point, then second summing point, here it will be a third summing point, and here it will be a fourth summing point. And then we have some takeoff point. This will be the first takeoff point, this will be the second takeoff point, and this will be the third takeoff point, this will be the fourth takeoff point. Apart from that, we are having some forward path blocks like G1, G2, G3. This is also going to be a forward path block G4 followed by G5. And we are having some feedback path block like H1, then H2, and then H3. So these things we need to observe very carefully. So step number 1 is that whatever the system block diagram available with us, we need to observe that block diagram very carefully, identify that how many number of uh, blocks are there in that particular system, whether they are forward block or they are feedback block, how many number of summing points are there, how many number of takeoff points are there, the way they are connected in the system, everything we need to observe very carefully. So identify the signals, variable, summing point, and takeoff point in the given block diagram that we have done. So the same system is available over here. Now in step number 2, what we need to do, we are going to represent each signal, each variable, each summing point, and each takeoff point by a separate node in the corresponding signal flow graph. So whatever the signals, whatever the node, or sorry, whatever the summing point or takeoff points or variables available in the block diagram, each one of them now we are going to represent by a separate node. So here I have mentioned some nomenclatures like this R of S is our first reference input, it will be like R of S only, and this Y of S indicate the final control output, it will be like this only. But apart from this, whatever the summing point and takeoff point we are having with us, that I'm going to represent by some certain sets of variable. Like here, first summing point is indicated by y1, second summing point is indicated by y2. Then in between these two block, that means a block of gain g1 and g2, we are having one more variable that that is indicated by symbol y3. In the same way, this takeoff point is indicated by variable y4 or by nomenclature y4. In the same way, this summing point is indicated by y5, then this will be y6, this will be y7, this will be y8, and here we are having y9, which is exactly going to be equal to y of s. Now what we need to do, we need to place them in their corresponding equivalent signal flow graph like this. So these dot indicate each node corresponding to signal, variable, summing point, and takeoff points available in the given block diagram. So this will be the first node corresponding to the reference input signal. This will be the node corresponding to first summing point. This will be the node corresponding to second summing point. This will be a node corresponding to a signal, or you can say intermediate signal, that is going to be developed between block of gain G1 and G2. In the same way, this Y4 indicate the node corresponding to this takeoff point, and so on. So if you apply that logic in step number 2, I told you that each and every signal, variable, summing point, and takeoff point we are going to represent by a separate node in signal flow graph. Then what we need to do in step number 3, whatever the blocks available in block diagram, that we need to represent, or that we need to replace by a corresponding branch in signal flow graph. तो जहां जहां पर आपको ब्लॉक डायग्राम में जो ब्लॉक दिखेंगे, अब उन ब्लॉक्स की जगह हम लोग क्या करेंगे, सिग्नल फ्लो ग्राफ में ब्रांचेस जो है वो ड्रॉ करेंगे. So the structure will be something like this. For example, in case of the block diagram, if you see here, we are having a reference input signal that is connected to summing point. So here we don't have any block. The moment we don't have any block, we will connect these two nodes by a branch of gain exactly equals to 1. That is important. In the same way, if you see, this will be your first summing point, this will be your second summing point, and in between these two summing point, we don't have any block. So what we are going to do, the node corresponding to first summing point, which is y1, and node corresponding to second summing point, which will be y2, we are going to connect them by a branch of gain exactly equals to 1. This topology we need to implement. In the same way, if you see the node corresponding to signal y3 and the node corresponding to second summing point, which is nothing but y2, in the picture here and here, in between these two nodes we are having a block of gain exactly equals to G1. So what we are going to do, these two nodes we are going to connect by a branch of gain exactly equals to G1. That is important. And the flow of signal is in the same way as they are mentioned in their equivalent block diagram. That is important. So this will be your step number 3. See, if you apply that particular logic, we will get this particular figure as an output. I hope this point is clear to everyone. Take your time, analyze this particular figure very carefully, because this is a very crucial step of converting block diagram into its equivalent signal flow graph. Observe the given block diagram very carefully. Represent each and every variable, then summing point, takeoff point, intermediate signals by a separate node, and then whatever the blocks available in the block diagram, represent them by a corresponding branches in their equivalent signal flow graph. That will be a step number 3. And then in step number 4, what we need to do, the gain of each block, or the transfer function of each block, we are going to represent them by a gain of that corresponding branches. For example, if you see here, in between node 2 and node number 3, we are having a block of gain exactly equals to G1. That's why the branch which is connecting node 2 and node 3, which is nothing but y2 and y3, we have connected a branch, and the gain of that branch is going to be equals to G1. In the same way, if you see node y3 and node y4, somewhere over here we need to take y4, and in between them again we are having a block of gain exactly equals to G2. So here we need to connect a branch of gain exactly equals to G2, and so on. So this topology you need to implement. That's it. So if you apply that logic, you will get this as a final answer. That's it. So if we have two or more than two nodes connected directly without having any block, so in those cases what we are going to do, we are going to connect them directly by providing a branch of gain exactly equals to 1. That's it. So if you apply that logic, you will get this as an answer. So this figure indicate the signal flow graph of our system whose block diagram is known to us. That's it. I hope this point is clear to everyone. If you know this technique, then it is very easy for us to determine its transfer function. How we can determine its transfer function? By applying Mason's gain formula. That's it. So this is what the technique is. If you know the block diagram, how to draw its equivalent signal flow graph. Now let us try to take one more example. This is very simple. Here we are having a system represented by a very simplified version of block diagram like this, and our objective is to convert this particular system into its equivalent signal flow graph. I hope this numerical will be solved by everyone. It is very simple. Here we are having input signal like R of S followed by summing point, and then here we are having a takeoff point, and then here we are having a controlled output signal. This indicate forward path gain, and this indicate feedback path of gain H of S. So if you apply those steps one by one, step 1, 2, 3, 4, you will get this as an output. I hope this point is clear to everyone. See what I told you, that identify the system. So here we identify that we are having two signals, input signal followed by output signal. So each signal and each variable we are going to represent by a separate node. So this will be your first node and this will be the last node. And then identify summing point and takeoff point. This will be the summing point and this will be the takeoff point. So each summing point and takeoff point we are going to represent by a separate node. And then we need to connect them by a branch. If they are connected directly without any block in between them, we need to connect them a branch of gain exactly equals to 1. So see, here we have taken 1 and here we have taken 1. But if you see, in between node corresponding to summing point and takeoff point, here we are having a block of gain exactly equals to g of s. That's why we have connected a branch of gain exactly equals to g of s. In the same way, between T1 and S1 we are having a feedback path. So see, T1 and S1 we are having a feedback path of gain exactly equals to minus H of S. See, minus H of S. That's why. So this is what a simple technique. If you apply this technique, you can easily find out the equivalent diagram of given block diagram into its corresponding signal flow graph. That's it. And once you know that signal flow graph, it is very easy to apply Mason's gain formula to determine its transfer function. That's it. Its history of signal flow graph and all, how to draw signal flow graph, or how to convert signal flow graph into its equivalent transfer function by applying Mason's gain formula. This portion we have already covered in our previous lectures. Now we are going to discuss in detail about the concept of sensitivity. And before that, we should know what exactly the feedback in control system, because feedbacks are normally implemented in control system just to minimize the effect of sensitivity. We don't want our system to be highly sensitive. So how feedback plays an important role to minimize the effect of sensitivity? So before that, first you should know what exactly feedback is and what are the different types of feedback. and if we apply negative feedback or positive feedback, what will be the equivalent gain of that particular system. So this portion we have already covered in our previous series of lectures. The thing is that we will make a quick revision of this, and then we will start the concept of sensitivity. So what is feedback? In any physical system, feedbacks are basically of two type: positive feedback system and negative feedback system. So what is positive feedback system? In case of positive feedback system, the nature of feedback signal is positive. That is important. So nature of feedback signal is positive. That's what is called as positive feedback system. Whereas in case of negative feedback system, the nature of feedback signal will be negative. That's what is called as negative feedback system. Now let us try to take examples of positive and negative feedback system. So this figure we have already taken. This is the example for positive feedback system. Why? Because see, here we are supposed to get a feedback signal which is nothing but B of S, and this B of S indicate your feedback signal, and here the nature is positive. That's why it is nothing but positive feedback control system. And if you apply elimination of closed loop over here, you will get the overall transfer function like this. So it is G of S upon 1 minus. See, for positive feedback system, you will get negative in the denominator polynomial function of the transfer function. So G of S upon 1 minus G of S into H of S. In the same way, if you have a negative feedback system, why it is called as negative feedback system? Because here, whatever the feedback signal which we are getting as an output, which is nothing but B of S, the nature of that feedback signal is negative. That's why it is called as negative feedback system. And if you apply elimination of closed loop over here, the overall transfer function in this case is nothing but G of S upon 1 plus. This is important. See, plus. Why it is plus? Because it is a negative feedback system. That's why you will get plus sign in the denominator polynomial. So uh, G of S upon 1 plus G of S into H of S, this will indicate the overall transfer function for this particular system. That is very important. Now let us try to discuss what exactly sensitivity is. Now, what is sensitivity? Sensitivity is nothing but a process through which we are trying to determine how the behavior of a system is going to change if some parameter of the system is going to vary, maybe due to internal disturbances, maybe due to environmental condition. That means, suppose we have a system, and because we have a system, it is made up of some parameter. So suppose we are having a system indicated by this block, and inside this block we are having some parameters which are responsible for the formation of that particular system. And we know that the parameters of the systems are going to vary due to environmental conditions. It may possible that the environmental conditions may arise due to internal disturbances, or it may possible that those environmental conditions may arise due to the external disturbances. But the thing is that if the environmental conditions are changed, the value of this parameter is going to change. And if the value of parameter of system is going to change, the corresponding output which is generated by this particular system when it is excited by some input excitation is also going to vary. For example, suppose this particular system is designed to generate output y for parameter p, but due to change in the environmental condition, the parameter of the system is going to vary, because of which the desired output of the system is also going to change. So instead of generating y, now it may possible that this particular system is going to generate output y dash. So this particular tendency is known as sensitivity. That means how or by what factor the output of the system is going to change if the parameter of that particular system is going to vary. That we can determine through sensitivity. So I hope this point is clear to everyone what exactly sensitivity is. So sensitivity is nothing but a factor through which we are trying to determine how the output of a system is going to vary if its corresponding parameters are going to change due to environmental conditions. That may be due to internal process, that may be due to some external unavoidable condition. So that technique through which we are in a position to analyze the change in the output of a system due to change in its corresponding parametric function or due to change in its corresponding parameter, that process is called as sensitivity, or that factor through which we are analyzing the behavior of that system is known as sensitivity factor. So the same thing is mentioned over here. Sensitivity is defined as a factor to access the variation in the output of a system due to change in its parametric function. That is important. And in order to overcome this particular effect, we need to use feedback mechanism. That's why feedback are normally used in control system, because see now, we don't want our system output to be changed if the parameters change. For example, if we design a system to generate y output when it is excited by input x. Now, due to some reason, if suppose the system parameter vary, maybe instead of having p, now the value is say p1. So corresponding to this p1, now the system is going to generate some output which will be y1, which is undesirable because we designed this particular system for providing output y. But due to change in the parameter of the system, even we apply same input, the system is not going to generate same output. Instead of generating y, now here it is going to generate y1. So this factor is called as sensitivity. That means by what amount the output of the system is going to change. That is called as sensitivity. And we want our system to be less sensitive. That means even though the parameter is going to vary by a small amount, the output will remain in the tolerance level, or the output must follow its desired value. And to achieve that, we need to apply the concept of feedback. Now, as I told you that in case of control system, we are having two possibility to apply feedback mechanism. We may go for positive feedback, we may go for negative feedback. Now we are going to analyze that. Suppose if we take positive feedback system, what will happen to open loop and closed loop control system? And suppose if we take negative feedback, what will happen to the sensitivity factor of open loop and closed loop control system? This portion is little bit theory, but it is very technical. If you understand this theory very effectively, then it is very easy for you to solve any numerical on sensitivity. So effect of parameter variation on open loop control system. So what we are going to do now, in case of open loop uh, control system, we are now going to vary the parameter, and we are trying to check if we vary the parameter in case of open loop control system, how the output is going to vary. In case of open loop control system, because the system is open loop, it has only forward path, and we know that forward path gain is indicated by symbol g of s. So if you apply that logic, see, this indicate a simple open loop control system. To that, this is r of s, your main reference input signal, and this indicate your control output signal, and g of s indicate the clock gain, which is nothing but forward path gain. Now what we are going to do in open loop control system, the overall transfer function is given by, see, suppose the overall transfer function is indicated by symbol m of s. So it is going to be like c of s by r of s, and this is going to be g of s. So this g of s is going to be equal to what? M of s. So this is for open loop control system. Open loop control system. Now what we are going to do, we are trying to calculate the output in this case. So output is going to be like input times the gain. See, input times the gain. That's it. So c of s is nothing but g of s into r of s. Let this will be your equation number one. Now what we are going to do, we will change the value of forward path gain, because ultimately what we are going to do, we want to identify that how the output is going to change if we change the parameter of the system. So here this g indicate the parameter of the system. So what we are going to do now, we are going to change this particular parameter by a small value. See, That value is nothing but delta g of s. And now we are going to calculate what will be the modified gain of the forward path. So modified word gain of the forward path will be like g of s, which will be the previous one, plus corresponding change in the forward path gain, which will be delta into g of s. Now based on this, let us try to calculate what will be the change in the output. So change in output is again indicated by symbol delta c of s, and it is given by c of s plus delta c of s. This is going to be like input multiplied by gain. Now here, whatever the gain which we have taking, this will be a previous gain followed by corresponding change in the gain. So g of s plus delta into g of s. I hope this point is clear to everyone. कहने का मतलब है कि आपके पास में जो गेन था उसको आपने एक सिंपल वैल्यू से चेंज किया, and that value is delta g of s. The moment you change this forward path gain, ऑटोमेटिकली इसका आउटपुट भी चेंज होगा. कितने वैल्यू से चेंज होगा? स्मॉल वैल्यू से चेंज होगा, दैट इज नथिंग बट डेल्टा सी ऑफ एस. तो अब हम ये कैलकुलेट कर रहे हैं कि वो चेंज वैल्यू ऑफ आउटपुट कितना है. दैट्स इट. So it will be like output in this case will be like input plus change in output, output plus change in output, which is going to be effective gain of the system multiplied by input. Formula तो वही है, output is nothing but gain times input. So here gain will be g of s plus delta g of s, because अब हमने gain को change किया, और वो अगर change करता हूँ तो output पे क्या effect आएगा वही हम लोग find out कर रहे हैं. So if you solve this equation, you will get this as an output. Now from equation number 1, g of s into r of s is nothing but what? C of s. So this g of s into r of s and this c of s are nothing but same. So we need to cancel out this. And finally, we conclude that the change in output due to change in forward path gain by a small value delta g of s is nothing but delta c of s, which is nothing but delta g of s into r of s. This will be your equation number 2. Now from equation number 2, we conclude that if the forward path gain of an open loop control system is changed, corresponding to that change in forward path gain, the output of the system is also going to vary. And this is what we need to study. So from equation number 2, it is very clear that the change in output is corresponding to the change in forward path gain. जैसे जैसे आप फॉरवर्ड पाथ गेन को चेंज करोगे, जिस पर्टिकुलर फैक्टर से आप चेंज करोगे उसके हिसाब से आपका आउटपुट भी वैरी होगा. वो हमने कंक्लूड किया. नाउ लेट अस ट्राई टू अंडरस्टैंड व्हाट इज द इफेक्ट ऑफ पैरामीट्रिक वेरिएशन इन केस ऑफ क्लोज लूप कंट्रोल सिस्टम. Now, in case of closed loop control system, now because we are having two possibility, because in case of closed loop control systems we have forward path as well as feedback path. In case of forward path, we are having a gain g of s. In case of feedback path, we are having a gain h of s. So here we are having two possibility. Either we can change the value of g of s, and let us try to find out what will be the change in output, that is delta c of s, or it may possible that we may vary the value of h of s, and let us try to find out what will be the effect on corresponding output. So let us take, I think, first case. So this is what our closed loop control system is, where this g of s indicate forward path gain, h of s indicate feedback path gain. This is summing point, and this is takeoff point. And in this case, or all transfer function is nothing but here we have taken negative feedback system. You may take positive also, but here for a reference point of view, I have taken a negative feedback system. So in this case, the overall transfer function, if it is indicated by symbol m of s, it is going to be like c of s divided by r of s. So it is going to be like g of s upon 1 plus y plus, because we have taken negative feedback system. 1 plus g of s into h of s. And suppose if you try to calculate the output in the previous case or the base case, it is going to be like c of s equals to input times the gain. So this indicate your gain. That this will be your equation number 3. Now again the same topology we need to implement, just the way we did in the previous case when we are dealing with open loop control system. the value of forward path gain is vary by a small value, the new gain will be like g of s plus delta g of s. Now corresponding to this, there will be a change in the output by a small value, and the value is delta c of s. Now let us try to calculate the new output of the system. So it will be like old plus change in output, which is going to be equal to input times the gain. Now the new gain will be wherever we are having g of s, that g of s we need to replace by new gain, which will be a combination of g of s plus delta g of s. So here, instead of writing g of s, now we are going to write g of s plus delta g of s. See, g of s plus delta g of s. In the same way, 1 plus, instead of writing this g of s, now we need to write g of s plus delta g of s. Rest of the thing is as it is. And if you further solve this equation, you will get this as an output. Now if you see in the denominator polynomial function, the value of this parameter is very small as compared to 1. It is very small as compared to 1. Hence we can ignore this particular term, and we will get this as a final answer. And if you further solve this by multiplying r of s to each component, you will get this as an answer. Now from equation number 3, see, equation number 3 indicate the output of a system in case of closed loop manner is g of s upon 1 plus g of s into h of s into r of s. So from equation number 3, this c of s and this term are nothing but same, so we need to cancel out them. And finally we will conclude a value of change in output like delta c of s is nothing but delta g of s into r of s whole divided by 1 plus g of s into h of s. That this will be your equation number 4. So equation number 4 indicate that the change in output in case of closed loop control system due to change in forward path gain. So here we have taken only one case, that suppose if you change the value of forward path gain to a small value, that is nothing but delta g of s. So how the output of the system is going to vary. That means what will be the expression for delta c of s, that we have derived from equation number 4. Now from equation number 2 and equation number 4, what is equation 2? If you go back, equation number 2 indicate, see, equation number 2 indicate the change in output in case of open loop control system when we change a forward path gain by a small value. Okay, and equation number 4 indicate the change in output, but in case of closed loop control system, again where we are going to vary a forward path gain. If you compare equation 2 and equation number 4, see, equation number 2 is indicate that how the output of the system is changed, or how the output of open loop control system is going to change if you change the forward path gain. And equation number 4 indicate how the output of closed loop control system change if you change the forward path gain. So now from equation number 2 and equation number 4, which one is more? See, the value of change in output is more in case of open loop system as compared to closed loop system. Why? Because in open loop we have only numerator, there will be no denominator, so it will be like delta g of s into r of s. But in case of closed loop control system, see, the entire value, that is delta g of s into r of s, is divided by this particular factor, which is nothing but 1 plus g of s into h of s. And I told you that we want to minimize this change in output, it must be 0. And to make this particular value 0, this particular value must be infinite, or practically as high as possible. That is important. Now in case of negative feedback system, we will get plus sign over here, but if you take positive feedback system, you will get minus sign over here. The moment you will get minus sign over here, the value of this denominator polynomial function is going to be less, and if this value is less, the value of change in output will be more. That is the reason in most of the cases we need to take negative feedback system, because the moment we take negative feedback system, we will get plus sign in the denominator. And the moment we will get plus sign in the denominator, if due to some reason the forward path gain or the feedback path gain of the system is going to vary, the output is again going to vary, but the variation in output is at least possible value. This is what the answer why we need to take negative feedback system in most of the cases. I hope this point is clear to everyone. So the same thing is mentioned over here. The output variation is more sensitive in forward path in case of open loop control system as compared to closed loop control system. So whatever I have explained just now, the same thing is written over here. And then we will define what exactly sensitivity is. So as I told you that sensitivity is nothing but a factor through which we are trying to identify that how the output is going to vary if we change some parameter of the system. So here, let us consider that we are having a variable. In our case, this variable is nothing but the output, uh, or you can say, let us consider that the variable of the control system is changes by a value a due to change in the parametric function. It may be a forward path gain or it may be a feedback path gain by a value k. Then the sensitivity of the system is given by percentage change in a divided by percentage change in k. And mathematically, we can write this particular term as do a by k or do a of k, or sometimes this is nothing but s of a by k. S indicates sensitivity, s of a by k. So we are trying to find out how the system is sensitive due to variation in the forward path gain, or you can say a feedback path gain. So this symbol s of a by k indicate the sensitivity of variable a with respect to parameter k. That is important. That means if you change this particular k, so corresponding to this change in k, how this variable a is going to vary, that we can identify through this particular formula. So in our case, this variable is nothing but output, and this parameter may be a forward path gain or it may be a feedback path gain. So if you change for forward path gain or if you change feedback path gain corresponding to change in g of s, h of s, how the output of the system is going to vary, that we can define through sensitivity. So this is the mathematical formula that we need to used in order to determine the sensitivity, maybe for open loop control system or maybe for closed loop control system. Now let us try to calculate the sensitivity of overall transfer function, which we have indicated by symbol m of s due to change in forward path gain, which is nothing but g of s. तो अब हम क्या करेंगे कि सेंसिटिविटी का फॉर्मूला या फिर सेंसिटिविटी फाइंड आउट करेंगे ओवरऑल ट्रांसफर फंक्शन का, अगर मैं मेरे सिस्टम का फॉरवर्ड पाथ गेन चेंज करता हूं तो। अब इसमें फिर दो केसेस रहेंगे। इट में पॉसिबल दैट वी मे डील विद ओपन लूप सिस्टम और इट में पॉसिबल दैट वी मे डील विद क्लोज लूप system. So let us take one by one those examples. So first we will define the general formula to calculate the sensitivity function with respect to overall transfer function, or sensitivity of a system with respect to overall transfer function if we vary forward path gain. So it will be like S m of g. So it will be like percentage change in m divided by percentage change in g. So it will be like dou m of s by m of s divided by dou g of s by g of s. Or it will be like g of s by m of s into dou m of s by dou g of s. That this will be your equation number 6. So this is very important formula through which we are trying to find out what will be the sensitivity of a system when we vary the forward path gain of that particular system. It may be open loop, it may be closed loop, that doesn't matter. The thing is that we need to apply this particular equation to calculate the change in the transfer function of a system due to change in its corresponding forward path gain, where m of s indicate the overall transfer function, g of s indicate the forward path gain of that particular system, and this particular factor indicate the variation of forward path gain with respect to change in the the variation of overall transfer function with respect to change in forward path gain. That means dou m of s by dou g of s. So let us try to take, if we have open loop control system. As I told you that in this case we are having two possible cases. It may possible that we may deal with open loop control system. It may possible that we may deal with closed loop control system. So first we are going to take open loop control system. So suppose we are having open loop control system. The value of m of s is nothing but c of s by r of s, which is going to be g of s. Now what we need to do? We need to put the value of m of s equals to g of s in this case, and try to find out variation or derivative of, or partial derivative of m of s with respect to g of s. Now see, m of s is nothing but g of s. So if you take derivative of g of s with respect to g of s, this factor is going to be what? 1. So if you apply that logic, put these equations in equation number 6, you will get the sensitivity, or you can say sensitivity of open loop control system due to change in forward path gain is nothing but 1. This is very important. 1 is nothing but highest possible value. That's why we can say that open loop control systems are highly sensitive, and this we don't want. We want to minimize this particular factor. We don't want our system to be sensitive. But this is not the case in case of open loop control system. They are highly sensitive. That's why their value is 1. Now if you take closed loop control system, now in this closed loop control system, again we are having two possible conditions. It may possible that we may vary forward path gain, or it may possible that we may vary feedback path gain, because in case of closed loop, because we are having two paths, so we are having two variation aspect. We may vary forward path gain, or we may vary feedback path gain. So first we will vary forward path gain, and let us try to check how the sensitivity will be there in that case. So in case of closed loop control system, overall gain is g of s upon 1 plus g of s into h of s. Now why we have taken plus over here? Because I told you that we want to minimize the sensitivity, and this is possible only for negative feedback system. So the moment we take negative feedback system, we will have plus sign in the denominator polynomial. This is important. So m of s equals to g of s upon 1 plus g of s into h of s. Now again apply the same topology. Take the derivative, and if you try to apply that logic over here, you will get the expression for this derivative is 1 upon 1 plus g of s into h of s whole square. Now use the same formula, because we are trying to find out the sensitivity of closed loop control system of entire transfer function with respect to change in forward path gain. So it will be like g of s upon m of s into dou m of s by dou g of s. So put the value of m of s over here. It will be g of s upon 1 plus g of s into h of s, and put the value of dou m of s by g of s from this expression, and try to solve. You will get this as an answer. So equation number 8 indicate the sensitivity of overall transfer function with respect to change in forward path gain, but this is for closed loop control system. Now if you compare equation number 7 indicate what? Sensitivity of overall transfer function due to change in forward path gain in case of open loop control system, which is nothing but 1. This is nothing but equation number 7. So from equation number 7 and equation number 8, what we conclude, that sensitivity in case of closed loop control system is going to reduced by a factor of 1 plus g of s into h of s. The same thing is we already concluded in our just 2 or 3 slides before. That is the reason we need to go for feedback mechanism, because the moment we go for feedback mechanism, we are having a flexibility to reduce the value of this particular factor by an amount 1 plus g of s into h of s. See, if we don't have feedback, the sensitivity is 1. The moment we have negative feedback, we are trying to reduce the sensitivity by a factor of 1 plus g of s into h of s. See, this will be in the denominator. So denominator get increased. So automatically the value of this factor is going to reduce. That's it. So this is very important. Sensitivity in case of open loop control system when we vary forward path gain is nothing but 1. and the sensitivity in case of closed loop control system when we vary forward path gain is reduced by a factor 1 plus g of s into h of s. And based on this particular statement, we have one simple theoretical question that was asked in previous year gate, that in case of closed loop control system, if we vary forward path gain, by what factor the sensitivity is going to reduced if the feedback path is negative? The answer is 1 plus g of s into h of s. Suppose if they ask for positive, it will be like 1 minus g of s into h of s. I hope this point is clear to everyone. Now, if you apply the same topology, but for feedback path, instead of taking forward path gain, if you take feedback path gain, the formula will be like this. So instead of having g of s, now we need to take h of s, because we are trying to find out the sensitivity of overall transfer function with respect to change in feedback path gain. So if you apply the same logic, now instead of taking derivation of m of s with respect to g of s, now here we need to take derivation of m of s with respect to h of s. You will get this as an answer. Now if you put this value in our base case, which is nothing but equation number, I think, 9. Yeah. So in this equation, put the value of m of s like g of s upon 1 plus g of s into h of s, and put the value of this derivation. You will get the sensitivity uh, in case of closed loop control system with respect to feedback path gain, like minus g of s upon, or g of s into h of s upon 1 plus g of s into h of s. That is important. So from this, what we conclude, that in case of closed loop control system, the sensitivity of the system is going to vary much more due to change in feedback path gain as compared to forward path gain, because the sensitivity of a system with respect to change in forward path gain, it is like 1 upon 1 plus g of s into h of s. See this equation, this equation. But the moment we are trying to calculate the sensitivity due to change in feedback path gain, here in the numerator we are having this particular factor. That means g of s into h of s. So I can say that the sensitivity of a closed loop control system due to change in forward path gain is less than the sensitivity of the same system due to change in feedback path gain. So कहने का मतलब ऐसा है कि अगर आप क्लोज लूप कंट्रोल सिस्टम में फीडबैक पाथ एलिमेंट को चेंज करोगे, तो उसके कारण आपका जो आउटपुट है वो ज़्यादा चेंज होगा एज कंपेयर टू द चेंज इन फॉरवर्ड पाथ गेन. दैट इज द रीजन जब भी हम कंट्रोल सिस्टम की बात करते हैं, दैट टू व्हेन वी आर डीलिंग विद क्लोज लूप कंट्रोल सिस्टम, we never try to change the value of feedback path element. The moment we change the value of feedback path gain, output is also going to vary due to a huge factor, because it is highly sensitive by a factor of g of s into h of s. So g of s into h of s times से आपका sensitivity बढ़ जाएगा if you vary the value of feedback path gain as compared to forward path gain in case of closed loop control system. So these are very important concluding statement, and based on that, it may possible that you may have theoretical questions in previous year gates. So finally we conclude that in case of open loop control system, this is very important. In case of open loop control system, the overall, or you can say sensitivity of overall transfer function with respect to change in forward path gain is nothing but 1. See, the value of sm of g is going to be 1. But in case of closed loop control system, the sensitivity of overall transfer function with respect to forward path gain will be like 1 upon 1 plus g of s into h of s. And in the same system, if we vary the feedback path element, the sensitivity of overall transfer function with respect to h, where h indicate your feedback path gain, is nothing but minus times g of s into h of s whole divided by 1 plus g of s into h of s. So finally, if you compare equation number 7, equation number 8, and equation number 10, which one is the highest? See, the highest value is this. That means open loop control systems are highly sensitive. But after that, this one will be the value comes into picture. That means sensitivity of overall transfer function with respect to feedback path gain in case of closed loop control system, and the least possible value will be this one, sensitivity of overall transfer function with respect to forward path gain in case of closed loop control system. For example, if you indicate this particular value by A, this particular value by B, and this particular value by C, so I can say that the value of A is more as compared to C, and this will be more as compared to B. So A is at highest possible value and it is 1. Then we have then we have C, which will be this, and then we have B, which will be this. So this is very important, and these are final concluding statement, and these are final mathematical equations that you need to remember in order to solve numerical on sensitivity, maybe for open loop or maybe for closed loop control system. I hope this point is clear to everyone. Now from this point onwards, if you are dealing with sensitivity, you must have this particular sense that what will happen if you change the value of system parameter, maybe forward path gain or maybe feedback path gain. In case of open loop, we have only one path, that's why we need to deal with forward path gain only. But open loop control systems are highly sensitive because sensitivity factor in them is 1. But in case of closed loop, the thing is that we need to take care whether we are going to vary forward path gain or feedback path gain. बट फीडबैक पाथ गेन का जो इफेक्ट है सिस्टम के आउटपुट पे ज़्यादा रहेगा बिकॉज दे आर हाईली सेंसिटिव ड्यू टू चेंज इन फीडबैक पाथ गेन एज कम्पेयर टू forward path gain. That is important. So in the next lecture we will solve some numerical on this, and then we will start one of the most important topic from control system that deals with the concept of time response analysis. Thank you.